Hey, Physics 102 students, this lecture is Chapter 16, Part 1. So I think Chapter 16 will probably take in 2 different sessions. Some very, very nice topics there. And some people actually go on to become like an audio engineer. So that, there are some places where the details that we will look at can be ferreted out in a much, much deeper sense. And so if you really kind of sort of like these topics, typically a university will be teaching a course probably called like the physics of sound and music, where, you'll really look at quite a bit of detail. We'll just be kind of scratching some surfaces here, but some very, very nice things here. So chapter 16, part 1 is what I'm calling this lecture. Let's first take a look at the velocity of sound waves. And, I think eventually we'll go to the laboratory and we'll actually, make these measurements here. And, the velocity of a sound wave, you should remember from chapter 15, what does the velocity of a wave really depend on? And, the velocity of the wave depends on the medium that the wave is really going through. And so I kind of want you to recall something here. And so let me kind of start scribbling some stuff down here. And, kind of recall here, the velocity of a wave on a string, something one-dimensional. Okay, so it's something that, gets used in something like chapter 15, and eventually we'll go to the laboratory there and also do something called Meldey's experiment. We'll be putting waves on a string and controlling them. So we'll be controlling, the 2 important aspects of the string. And so if you remember what this is, there's a square root here, and on the top of the square root, I'm not going to put a T here because it starts looking like period and things like that, but it's really the tension. And that's in newtons that you put the string under. Okay, so the tighter you've got it, since it's on the top of a fraction, the faster the wave is going to go. And on the bottom was mu, which is not a coefficient of friction, but that's really the mass per unit length. And we're going to have that mass in kilograms, the length in meters here to match up with the tension above. But I think if you follow the units through carefully and you take that square root, you're going to see that you truly do get meters per second here. Okay, so this is something that we have seen before. Now, when it comes to sound waves, the velocity changes a little bit every single day. Because the stuff that the wave goes through changes a little bit every single day, right? So no air molecules, really no sound waves, right? In space, no one can hear you scream. So if you remove the medium, then the wave that we call sound, really ceases to exist here. But really look at that form of the wave on a string and how we find the velocity. That's not really a law. But if you kind of do enough hand waving and things like that, like you see in your textbook, you can get pretty close to a derivation. But like I said, it's not really a law or anything like that at all. Now, when it comes to something like a sound wave, the form is going to look very, very similar to that. Okay. So the velocity of a sound wave, it too is going to depend on the material, but maybe it doesn't surprise you too much that there's a square root here, and inside the square root is a fraction. So it really kind of comes down to really kind of the same type of form here. And now you start wondering, well, you can't put air molecules really under tension or anything like that at all, and then that's kind of true, but usually in a textbook you'll see something like a Y here, and that's really stands for something called Young's modulus, which is typically some kind of constant that gets hooked to the material But you usually go to the laboratory, you make some measurements on Young's modulus by getting the material, putting under various stresses or strains and things like this. So that's a constant that we really kind of look up. And then on the bottom, you need kind of the counterpart to mass per length. But since air is really a three-dimensional character, it doesn't surprise you that what you really have here then is the density on the bottom. And that this really does work for different materials. That is, sound can go through something like air, but you can go up to the railroad tracks, down here by 9th Street with just a hammer, and you can whack it, the steel rail with a hammer, and you can have somebody downline, kind of feeling that rail, and you'll get an indication of just how fast that pressure wave, that compression wave that you put through the material by hitting it, right? All the molecules slam into each other, and then that domino effect kind of races away, how fast that goes. And so it really does depend on the material. So the denser you are, then something starts happening to the velocity of these waves and so forth. So I just kind of went to the textbook and looked at a couple of these constants here. So for example, for aluminum, a very, very common metal, and the velocity in aluminum. So how sound waves go through aluminum? Well, you might have something that you have a piano at home, you might have a tuning fork, and a tuning fork typically are made of aluminum, and you just kind of tap them on the bottom of your shoe, and you can kind of put them up to your ear. And it really looks like kind of like a fork, kind of like the peace sign, and the two pieces are wiggling, and so they push the air at a certain rate, and it's supposed to be the same rate all the time. And so if you have something like a C note tuning fork and you tap it, it starts vibrating and starts pushing the air at that same rate, and then your ear starts vibrating at that rate, and you go, oh, okay, this is like middle C, this is like 260 hertz or something like that. And then you hit the C on your piano. If it sounds the same, then you're good to go. And if it doesn't sound the same, then you have to adjust the tension on the string, right? The piano is really a stringed instrument. And by changing that tension, you should be able to get this thing to be now in tune. And of course, you might have to do this with all 88 keys and so forth. But for aluminum, when you look up, some of these constants here, I end up with something out of your textbook, something like 7 times 10 to the 10th for Young's modulus. And the density here is something like 2.7 times 10 to the 3, and that's kilograms per cubic meter. And, when all is said and done, this comes out to be about 5,000 meters per second. Okay, so this is a big number, right? This is what, 15,000 feet, a little bit more than 15,000 feet per second. So this is about 3 miles a second. So it goes very fast through a solid, which might make conceptual sense since the molecules are so close together. It's very easy for them to knock the neighbor, and you kind of have this domino effect. And that is, right, the wave going through the material. And that's what creates, the little ping sound, when you're down at the other end. You might hear this. Or like in the physics lab, a lot of times the ring stands that you just stick in the middle of the table to, hold up springs and things like this. Typically those things aren't going to be made out of aluminum. It's lightweight, it's cheap, it doesn't rust. And, you can just kind of tick them with your finger, and they'll give off a ping. Now, that ping that you hear is the vibrations come through the air, but, you could detect how fast, those sound waves go through that material. And it's something like 5,000 meters per second. Now, if you go, and I think it's one of your homework problems, you just kind of go look up the constants for air. For air, you get something like 340 meters per second. So it's a factor of 10 less than this. So when you get the air molecules, and they are much, much less dense, the the velocity starts dropping off because that Young's modulus, then, or for something, you know, maybe like air or something like water, then you might be looking up the bulk modulus for these. You know, that has everything to do with how fast these waves can really kind of go through the air. So most of the time, you know, the velocity of sound in air is just about 340 meters per second. And you will see some sort of formula in your textbook, and a lot of times an atmospheric physics book may have something on this as well, where, you know, a lot of times they'll start with 340 meters per second or 343 meters per second, and then there's a plus or minus, and there's some sort of correction factor that might have a term with temperature. There might be a term in there with humidity, and those things really kind of play into how fast sound waves go. But for the most part, you know, the speed of sound down here close to sea level is something very close to this 340 meters per second, which is, you know, somewhere around 700 miles per hour. And, you know, we call this Mach 1, the speed of sound. And, you know, a number of people in the mid 1940s, you know, really probably lost their life trying to get an airplane and or a jet. Eventually, it's going to be essentially like a rocket plane, the Bell X-1, that will fly faster than the sound that it makes. And it's an interesting phenomenon when you break the sound barrier, that there's this pressure wave that you push through. And, you know, what you do is you get that sonic boom, right? You get this big, loud crashing sound. Very interesting, you know, how that was kind of done. And then, you know, it was kept very secret for a few years, for the people that designed that craft, and for Chuck Yeager who flew that craft. But so Mach 1, you know, really does kind of change, you know, a little bit every day. But for the most part, you know, I would think that most fighter jets, you know, in today's world, all can easily surpass that number. You know, a lot of them probably are able to go, you know, Mach 2, 1,500 miles per hour, something like that. I would think, but, you know, sometimes being more maneuverable might be better than just straight speed. And still today, I think the SR-71 aircraft, you know, showed up and did a flight, and, you know, somewhere around, as I recall, something, you know, like 3,000 miles per hour. So, you know, if 700 miles per hour is Mach 1, you know, the thing is you know, it's you know, it's doing Mach, you know, 4 or 5 or something like that we know about. You know, what it can really do, you know, maybe some of those things are really kind of kept a little bit secret and so forth. So some interesting things though with really how you can figure out these velocities through materials, and how similar that looks like to the velocity in a string. Well, after all, a string is just another material, right? So somehow those forms should all really look, you know, pretty close to each other, and, you know, pretty easy to use. Let's take a look here at how humans perceive sound waves. Okay. There's going to be a concept here, and it may be a new concept for many of you. And so, you know, it is something that you want to memorize, and that's this idea of intensity. I can't really think of a place where intensity shows up in Physics 101, but it's going to show up a couple times here in Physics 102. And it really is the right concept when it comes to waves and the perception of waves and so forth. You need to come up with, you know, the right concept, that you're making the right measurement that's really describing, you know, what you want to be talking about. So the intensity of sound waves would be something very close to the idea of kind of how loud is it. This is kind of a perceived loudness. Okay, not the frequency. Frequency, you know, little boys, little girls might have a high voice. They might be able to, make beautiful singers in a choir because they get hit these high notes. And typically, as you get older, the voice box changes and so forth. And now, usually, your voice goes a little bit lower. That's frequency that you can produce, from the voice box, and that's worth maybe describing a little bit too. But that's not this idea. Intensity really means sort of this loudness. And, most of us have had some sort of experience. Maybe you're in fifth grade and somebody, that you don't recognize kind of comes into your classroom. Maybe there's two people and, they whisper in the teacher's ear, then they kind of point at you, then they kind of pull you to the classroom and they walk you outside and, they put you in a trailer. And there might be a few other people in the trailer and they put these little earphones on and, they ask you to raise your hand if you can hear the little beeps that they're going to be producing. And so really what they're doing, I think, is two things. One is they're trying to see, can you hear high frequencies? Can you hear low frequencies? And I think we'll talk about that here in a moment. But then can you hear, or how low of a volume or a sound level can you really perceive? And so people have been doing this for a long time. And so, everybody's ear is different. Physiology for one person to the other is slightly different. But, we've come up with, a couple of numbers here that start describing at least probably the average human being when it comes to this idea of intensity. But intensity, we'll use the letter I for that. Intensity is defined, and I think I would memorize this. This is an important concept, is power. Okay. And it's power per area. And so power in Physics 101 was in watts, and that's exactly what this is. And area is in square meters. Okay. And then, you might recall that a watt is really a joule per second per square meter. But that really is what we mean by intensity. Okay. It's how much energy is there hitting some sort of, maybe if you're perceiving it, your eardrum per second per that amount of space here. And, we make these measurements on people. What we have is something that we call the threshold of hearing. And these would be the very, very dim sounds that the average human being can just kind of barely hear. And then on the other hand, you've got sounds where when you experience it, it'll probably leave like a physical lasting perception, like ringing in your ear, maybe many exposures, could lead to the lessening of your hearing or, the loss of hearing. And that's really called the threshold of pain, where you can physically kind of feel this sound wave and it leaves, this lasting impression. You go to a rock concert. If you just happen to be in the wrong place where maybe the PA system is really, really kind of focusing, a lot of these waves, you can go home, your ear still ringing, you could, sleep, normally through the night, you wake the next day, and you still can hear this ringing here, that's, what we call this threshold of pain here. But those are really measurements in this thing called intensity. And what, the typical person barely hears, the threshold of hearing, we call that I0. That's kind of the start of where you can just start picking up, very, very faint sounds. And when you measure that, that's something close to like 1 × 10⁻12. Okay. And intensity is in this watts per square meter. So right now, I don't know if I have a good feel of what that number really means, but maybe as I start playing with it, it'll kind of start making some more sense here a little bit. Now, where you start getting the ringing in your ear and those types of different perceptions, where people call this the threshold of pain. That intensity is something closer to like 1 watt per square meter. Now, when you take a look at this, you can see that the engineers and the scientists are probably not going to be happy dealing with the scale here from what you barely hear down at the bottom to the top, where you are creating some sort of physical sensation in the person's eardrum and so forth. There's a difference of 10 to the 12 powers. That's a trillion difference. This is just screaming for some sort of compaction of the scale here, because human beings just don't like numbers that are spread out over a trillion or anything like this at all. And so what we've got is something called a decibel scale. And the decibel scale is kind of like the Richter scale that geologists use to describe earthquakes. Like a 5 magnitude earthquake and a 6 magnitude earthquake. They're not really kind of like 1 apart. They're really more like 10 apart or something like that. It's really some sort of log scale. And that's what we need here. We need to cut these powers of 10 really down. And to do that, we've got this thing that we call the decibel. Sound level. And the decibel sound level, decibels, is usually measured in dB. And here's how we end up cutting down these numbers to some kind of scaling that really kind of starts making, maybe a little bit more sense here to human beings. What you really want to do is get that 1 times 10 to the minus 12 watts per square meter. And you say, that's the beginning of my scale, where people just kind of start hearing or picking up, some sort of really, really faint sound. You might want to kind of call that, scale, I don't know, like 0 or 1 or something like that, right? And then the top of the scale, something like 10 would be good, like they did with earthquakes. Like the Richter scale kind of goes from 0 to 10 for the most part, or 0 to 100 or something like that. And what ends up happening is that we've got something here called beta, which is the decibels, and it's 10 times the log. And if you don't write the base of the log, typically that means that you're just assuming that it's log base 10. And when you do this on your calculator, I think that's what you want to do. So make sure that it's log base 10. I think most calculators, mine's got 2 buttons as I take a look at it here. And I sort of see a LOG button, and the LOG button does mean log base 10. And then I also have the LN, which is the natural log, which is base 2.71, so forth, because it comes up with something that compounds continuously. And so this is really log base 10. And what you do is you've got this fraction in here, and you compare everything really to what it is that we can barely hear. So here's the intensity of the the sound wave that you're perceiving, and on the bottom what you always do is put the threshold of hearing, right? So the number down here is always going to be 1 times 10 to the minus 12 watts per square meter. And what this does is get all of those intensities that are varied over 12 powers of 10, and it really will compact them. So, for example, let's say that we perceive or we measure, some really small intensity, like what you barely can hear. Okay. So that's what you are perceiving, that's what you're measuring. This is going to scale it, this little bit of mathematics here. And so what we're actually perceiving, what we're actually measuring goes on the top. The bottom is always the same number. Everything's compared to what we barely hear, which really kind of makes sense here. And so this thing is really unitless. Units really kind of go away. And inside of there, what you get is, 1 times 10 to the minus 12 divided by 1 times 10 to the minus 12 is 1. Right? So if you, can't remember how you do your logs, that's going to tell you something like 0, because you're really just looking at exponents and so forth here. Right? So this thing right here really gives you a 0. So as you barely hear, when you scale it, it goes to 0 decibels. That's the beginning of really the scale. Now, if we put in, some sort of perceived sound here, that is quite a bit more intense. So, for example, I'll try another example here in a minute. Let's take a look at this. This is kind of showing up right here. And, it does show that human beings' perception of sound is a little bit frequency dependent. But here is the decibel scale. And, what we barely hear down here, we just kind of show that, what we barely hear is really a 0. And the threshold of pain is kind of up in here at 120 decibels. So it's not a perfect scaling like between 0 and 10 or 0 and 100, but it's pretty close to something like that. So when you're down at low numbers, 20s, 40s, 60s, those are kind of typical everyday numbers of conversations and things like that. And, as you start getting to louder and louder sounds, your textbook will have some sort of little graph there where it'll talk about probably, jet engines, jackhammers, things like that, where the people that are around those types of noises constantly probably wear some sort of little foamy plug that they can put in their ear, and then they probably put earmuffs on over that as well to protect their hearing. So if you're kind of on the tarmac and you're directing the jet engines, and you're right kind of down there close to that jet engine level, right, you're really going to want to be protecting those people here. But, this graph that you've got here in your textbook says that, kind of the top of our scale starts getting close to something like, 120 or something like that. So let's say, for example, that we actually perceive something at, 1 watt per square meter. Where does that land on our decibel scale? And what we always do is use something like this. And what we're perceiving goes here on the top, or what we're measuring. That's watts per square meter. That's a perfect W right there. And on the bottom is always the same number. We always compare to what we can barely hear. So those cancel out. And so 1 divided by 1 trillionth is a trillion, right? So what you really get when you take the log base 10, right? The log base 10 is going to knock out, 10 to the 12. It'll knock out that 10. It leaves you just that 12. And so I think on your calculator, when you try this, you're going to get 12, but you still have this 10 out in front. So 10 times 12, and that puts you at about 120 decibels. This is kind of the top of the scale. Now there are noises that probably can get much louder than that. Maybe something like the space shuttle taking off, certain explosions or something like that. I think this is probably pretty good what we see in the textbook here, that most of the sounds that we would consider normal are falling in this range, 0 to 120 decibels or so. Certain places in the concert hall, maybe more than 120, in certain places maybe less. It will depend on, just how focused the PA system is, or whether it gives you, excuse me, a nice, free field or whatever. And you can kind of see that, there are some frequencies here that people might hear better than others, because for each line there, we do see a dip, right? Looks like that dip is getting close to around 4,000 hertz or so. And where the intensity or the decibel level is slightly less, which is kind of interesting here. There's kind of the sweet spot here for human beings. Okay, so the decibel scale then is going to then really, give us numbers that are kind of reasonable, right? 10, 20, 30, 40s, that kind of stuff, instead of, we've got these big, huge powers of 10 and stuff like that. But, I do have here that a typical, it's just kind of interesting to see how this works. A typical jet engine is something close to, if you're right on top of this thing, 100 watts per square meter. And I kind of want to use this number here because it's a really good comparison to what we really have, up above here at 1 watt per square meter. And if you're going to try to scale this to see how many decibels this is, it's 100 watts per square meter. On the bottom is what we always have as threshold of hearing. And, so if I'm going to get 100 on my calculator divided by 1 times 10 to the minus 12, I'm going to take the log of that. I get 14 times 10. I get now 140. Okay, so something to take away here. Take a look at those two numbers. And then take a look at that number there and that number there, right? What I did here is I increased the intensity of the measured or the perceived sound by 100 times, right? From 1 watt per square meter up to something like 100 watts per square meter. So something got bigger by 100 times, but it's crammed down essentially into this log function. And what you get is an increase of 20 decibels. Okay, so an increase of 20 decibels is really huge. I think the typical person probably can easily identify a difference of about 2 or 3 decibels. 2 or 3 decibels is quite a bit. And so, I'm trying to think, where you kind of go, and you might see decibels or something like that. But it does seem like the last time I was shopping for a dishwasher, they always all want to claim how quiet the dishwasher happens to be. And there was a decibel number on the dishwashers. And, sometimes the salesperson would say, hey, look, this one is, rated at 50 decibels. And I said, yeah, but look at this one over here. This one's, 40 decibels. And he says, well, that's only 10 decibels difference. 10 decibels, 10 decibels, you can hear that next door, right? So it's a huge difference, just a few decibels. And so what might be very instructive here for you to do, this might be something you might want to know, is try the decibel scale here with maybe an intensity of something like, let's compare this up here to, let's say, 2 watts per square meter. Double, right? Double the intensity. Doubling the intensity is a big deal. See how many decibels difference you get when you put in 2 decibels. Because, 2 watts per square meter. See how many decibels that turns into. Because, it's bigger than 120. It's certainly less than 140. But I think, when you typically double in intensity, you only get a difference of about 3 decibels or something like that. And so 3 decibels is, quite a big difference that, people can easily perceive that. So give that a shot and see if you don't get something close to, maybe, I don't know, 123 decibels or something like that. I'm kind of guessing you might be kind of aiming for. It kind of seems like that's what is coming to my memory, that when we double intensities. Yeah, sure enough. Yeah, I think you only get a few decibels increase here. So give that a try and see if you can't do that comparison there on the decibel scales. Now, frequencies. When you go out to the trailer when you're in 5th grade and they put the little earmuffs on you and they play these little beeps for you, part of what they're doing is trying to see, if you kind of have the normal frequency range that you use here. And, depending on your source of where you're looking at and that sort of thing, humans, on the low frequencies, it might be something like around like 5 hertz or something like that. And on the high frequency side of things, some human beings say that they can perceive 20,000 hertz. Okay, so there's a kind of a big difference between the low and the high here. My hearing doesn't go up to 20,000 hertz. Some students tell me that they can actually hear 20,000 hertz, and that's something we can actually try. Right? We can just get a function generator and we can just push a speaker at any rate that we want and sort of see what it is that you can hear here. But is in my kind of haphazard measurements with students over the years, 15, 16, 17,000 hertz, most people start saying, yeah, I can't hear that anymore. Now, if you go above this 20,000 hertz mark, people start calling this now ultra high frequencies, or it's ultrasonic or something like that. It's beyond the hearing of most human beings. And so something like the motion detectors that we use in the laboratory, they're operating at about 30,000 hertz. They put out a sound wave. And, the little computer knows that sound is traveling something close to 340 meters per second. And it hits something and it bounces back. And the minute it sends out a sound wave, right, the clock kind of starts. And when the echo comes back, the clock kind of stops the timer, and then it knows really how far something is just based on distance equals rate times time. Right? So it knows how fast it's traveling. It's got the clock. And so, those things are operating at 30,000 hertz. We're not hearing them make noises, but maybe when we're making measurements in our lab, all the dogs, and then maybe they're all howling and stuff, maybe they can hear, those frequencies. But like a dog whistle typically sounds pretty silent to most people, right? We don't hear it, but the dogs do hear that. They can hear higher than something like 20,000 hertz and so forth. But I think typically humans have been, gathering, most food, over, the last, hundreds of thousands of years, and we hunt, with probably our eyesight mostly, right? So we have not bad hearing, but there are certainly animals out there that probably have a more extended hearing range, and maybe that makes them in some ways a better hunter, or if they are a little bit more skilled in using those sounds that they hear for their survival. And and we'll find that some animals may have a wider range of the light waves that they can perceive with their eyes compared to what we can. So, we're not the end all to, perceiving sound waves and or, light waves or anything like that here at all. So, I think for most people, though, they're going to fall in this range. And, I kind of think that something like on a keyboard, something that people call, middle C is just about 260 hertz. And so, you're going to have a C note that's lower than this on the keyboard. You're going to have many C notes that are higher than this, because every time you kind of change like 8 white notes, you kind of hit another C note. But so most music is probably being played in the hundreds of hertz and probably the low thousands of hertz. So those mid-range frequencies, 4 or 5,000 hertz, are there's going to be a lot of instruments that can live in there without any problems and things like that. And something like the bass notes, those will be in the 100 to 200 hertz range, and so forth. And humans just typically don't have that much problem perceiving these frequencies here. Okay, let's see here what's going on next here. The free field. Now for us, we're not going to use anything other than the free field. But people that go into something like the study of acoustics, they will be very concerned with non-free field environments. And a free field really means that when you start a sound wave, for us, we're just going to assume that it moves in all directions the same speed. So essentially, it's making a sphere in 3 dimensions, right? The sound wave, the energy is on the sphere, and the sphere gets bigger and bigger and bigger. So the further you are away from what created the sound, the source of the sound, maybe it's a speaker or something like that, the energy now is on this sphere that keeps getting bigger. And so it becomes, less perceptive to, human being and so forth. So for us, the free field, we will always assume that the sound waves move out in a free, unimpeded sphere. Now, in something like an auditorium, that's probably not true, right? You've got walls, you've got maybe 1,000 people sitting in chairs, you've got a ceiling, you've got reflections, and now you're probably dealing with something that's not that simple to deal with. And something like a free field. But the free field is, we're going to assume here that sound waves move out on a sphere. And so, for example, let's just say, for example, let's say you've got a speaker here. And so the sound waves are going to just, be moving out, like so. And here's what we can kind of do with this here. So stereo speakers, a lot of people have a stereo receiver that might be capable of 100 watts. That's 100 watts is pretty good, right? The people on another block can hear 100 watts going, if you've got this thing turned up really, really well. Don't ask me how I know, but let's see here. Let me get a different color here. And, let's say that let's just say that you're here at maybe 2 meters, and let's say that this is a 40 watt sound wave or something like that. Okay, and if your ears right here, so here you are, and your ear is a 2 meters from this speaker that's producing a 40 watt power in terms of the wave. You should be able to kind of come in here and say that we're just going to say, well, okay, how do we sort of handle something like this? But intensity is really your power per area. And so what you've got is 40 watts here. But as it moves out from the speaker, the sphere gets bigger and bigger and bigger. And so what you have here is a 4 pi r squared, and that's really right the area of a sphere. And so if I've got something like 40 watts, I've got 4 pi, and I'm like 2 meters away from it. Right, 2 is going to get squared. This is going to tell you the intensity you know, where this is going to fall kind of on the scale here. So I'm going to try this 40 divided by 4 divided by pi divided by another 4. You know, I think I'm getting something like this, just about something like this. Watts per square meter. To me, this is pretty loud, right? 1 watt per square meter, and this is, you know, 80% the way there, can cause pain and so forth. So, you know, even indoors, something like a 40-watt speaker, if it's, you know, hitting you with, you know, full energy, can be quite a bit. Now, what if you say, okay, that's too close, and you come out here and you sit from the speaker. Let's say that you're now 4 meters away. What happens to the intensity of the sound wave then? Okay, so now you're going to have 40 watts, but it's spread out excuse me, over a much larger sphere. Now you've got a 4 meter radius, and that's going to get squared. So I'm going to get 40 divided by 4 divided by pi, and I have to divide it by 16 as well. And now I've got something close to like 0.20, you know, watts per square meter. So what happened? What happened to the intensity when I doubled my distance? When I doubled my distance, it looked like the intensity went down by a factor of, looks like 4 here. Right? And I want you to try this on your calculator and see if you're not kind of catching on here. You can grab a different color here. This on the decibel scale, 10 times log, and I've got 0.8 watts per square meter. And on the bottom, I've got 1 times 10 to the minus 12 watts per square meter, and see where that falls in the decibel scale. So 0.8 divided by 1. I'll try this, see if you can kind of work along here. And you know, I think this is kind of like 119. Here I doubled my distance, and if I put this on the decibel scale, I've got 10 times the log, 0.2 watts per square meter. And on the bottom, and I'm not worrying too much right now about significant figures or anything like that at all, but 0.2 divided by 1 to the 12 minus, take the log of that, it's 10. Yeah, very interesting. So if you double your distance, it looks like your intensity goes down by a factor of 4, and it looks like your decibels go down by 6 decibels. And so that's quite a difference. You would definitely hear and feel a difference there. Something very interesting on how people deal with how humans actually, you know, perceive these waves which are around us in our atmosphere. So as long as we've got this medium called the air, you know, we're going to be perceiving sound waves. You go in space where there is no medium, you know, there is no sound waves. So, you know, I don't know what that means for, you know, all of your science fiction where the, you know, the spaceships are making noise and the little rocket or the little laser guns make noise. When they blow up, they make noise and all this. So, yeah, Hollywood is not big on science. So anyway, some very interesting facts are kind of coming up here. So yeah, make sure this is kind of sinking in and you're starting to feel comfortable with this here. Okay, now interference. We have dealt with this idea a little bit, but I'm going to look at this differently for sound waves. And if this idea that I'm going to use here makes sense to you, because it's not really deep, it's not a very complicated set of circumstances that we need to really be able to look at the interference of sound waves. But if it makes sense to you, then you're going to have just a very easy time when it comes to something like even light waves, because we'll look at it, much the same and so forth. So, what I would do here to create definite places of constructive interference and definite places of destructive interference, the most simplest thing that you can do is to have one coherent source of waves. And we'll talk more about what coherent really means here. But it's very easy to do with sound waves, because you just get something called a function generator, which is just an electronic generator that can swash electrons back and forth at really any rate that we kind of want. So there's some very fancy electronics inside of it that can do that. And then you just hook that to a speaker, and then the speaker will vibrate at exactly that rate. So if you dial in your function generator and you say 500 hertz, that means the electrons that are going through the wires that come out of this box are shaking back and forth at 500 times per second. If you hook it to a speaker, then the cone of that speaker vibrates back and forth at 500 times per second. Then the sound waves feel that pressure difference of 500 times per second. And then right here on your eardrum, right, it starts vibrating then at 500 times per second. And so you have this duplication of frequencies here from the function generator. And what I want here is I want two speakers connected to one function generator, and then I don't have to really worry about having non-coherent sources and then the phasing of these things, anything like that at all. And so a function generator, sometimes the engineers will kind of draw these things just as a little box here, and they'll put like a little sine wave here. And this means that something that can generate some sort of sinusoidal wave, or maybe a square wave, or maybe a triangular wave. And those would all sound a little bit different here. And what you do here is, you just get a wire kind of coming out of this, and you just connect it to a speaker. You get a wire here, and you connect it to another speaker. And let's say that, the wave that is coming out of these speakers, since they're both connected to the same function generator, they're producing the same frequency, they're producing the same wavelength, and we're not changing the dial, right? So this is just one frequency. And so what you hear is just kind of like a hum, just a, and that's what the machine is kind of making. Now you can dial up to make other sounds and so forth. But let's say that there's a spot out here. So maybe that's one wavelength. Here's two wavelengths. And here's three wavelengths. And there's a receiver right there. That receiver might be your ear. It could be, an actual electronic receiver or something like that. And notice that the other speaker, it has a longer path. Right, the waves to hit this spot right here, the waves here have got a different path they have to take to get to that spot. Now they're both producing exactly the same size wave. So I'm just going to kind of do the best I can here drawing this. But let's say that up here there's one whole wave, two whole waves, three whole waves. Now on the bottom down here, let me kind of change this color here so it stands out a little bit. Let's say that holds a wave, one wave, two waves, three waves, two waves, three waves, four waves. So here we have three full cycles. Down here we have four full cycles. Okay. Now there is nothing magic here about the number 3 or the number 4. It's just I just chose some number that I thought I can kind of draw here. But really the important word here is full. That I've got full cycles at this one location in space. Okay. So this is spatial interference. That is, I can move my receiver around, and I would not have this condition here. Okay, now this condition that you're looking at here, this would be constructive interference. How would you know? These are sound waves. It would be loud at that spot. Okay. How do I know this is constructive interference? Because each wave has completed the cycle. And the word that the physicists would use here is that at this location in space, at that spot right there, the waves are in sync. And they're doing the same thing at the same time, at the same place. And the word is they're in phase. Okay, so if they're in phase, you have a spot of constructive interference. Okay. Can you think of a place that would essentially guarantee constructive interference under these circumstances? Okay. And, you know, I think I can quickly probably imagine something like that happening. Where could you be guaranteed of placing your receiver? So here's my speakers. I kind of think, right, the place that would guarantee it would be right in the middle of the speakers, where this path length, and that's the important thing here, this path length is identical to that path length. That guarantees no matter where the waves are in their cycle, they arrive in sync or in phase. So maybe it could be that, you know, we only have like half of a wave completing itself here, but they are here in phase. Up here, they are in phase. And if they are in phase, we say that these are examples of constructive interference. And I'm not sure what my pen is doing here. Interesting. Okay. Now, if you wish to create or to find a location in space where the waves are out of phase, you would have a spot of destructive interference. If you want complete destructive interference, the waves need to be completely out of phase. And let me kind of show you what that might sort of look like here. So for example here, let's get an example of destructive interference. How about this? So we have our sound generator. We've got the function generator here. And it's hooked to the speaker here. It's connected to a speaker there. And let's say here. So we go to this spot right here in space. And that spot right there, let's say that holds one full cycle, right? One full cycle. But you see the path coming from the bottom speaker is longer, right? So the wave has to travel further to get there. And let's say that that happens to be one whole wave, and we have just a half wave, right? So here we have 1.5 cycles. But essentially, at that location of space, one wave is diving down where the other is starting its rise up. And at that point, they are out of phase with each other. They are completely out of phase. And so completely out of phase, this would be total destruction of the waves at that location in space. What would that mean for you? That would mean that if you put your ear there, there would be no sound. Okay, so if you can hit that spot exactly, there would be no sound. And so, are you worried at home, when you're standing between two speakers, that you hit a spot and you can't tell that the stereo is even on, right? You're at a spot of destructive interference. Well, that just never happens at home. It'll never happen. Well, why? Well, if you hit destructive interference with one ear, maybe 6 or 8 inches away, your other ear, the mathematical cycling of these two waves will be in different places. And so you may not have complete, destruction of the waves at the other ear. Plus you get reflections off of the walls, the floors, and everything like that. And you have to have all those waves to be completely out of sync or out of phase there. And so this is very difficult to do with sound waves because, right, there's just so many echoes for us to be dealing with. But here we would say that they are out of phase. And but if you would put a little receiver in that spot right there, and you just turn them on, and so the first waves that hit that spot are the ones that travel directly. Now, some waves in the free field are going to hit the ceiling, they're going to bounce down. They're going to hit a small amount of time later. Some might hit the floor and bounce up, but for a very small amount of time, you would perceive, no sound level there at all, which is kind of interesting until maybe, the reflections kind of get into that spot and things like that. So very difficult to do and to demonstrate with sound waves, but very easy to do with light waves, because light waves, we can get rid of the reflections and so forth. So it's much easier to really be dealing with them. Now, if these couple examples here make sense to you, then you really kind of got the concept here, right? They don't have to travel the same distance to be in phase, but they have to have the same phasing or be in the same part of the cycle to be in phase. And for us to have this condition of constructive interference, that's what you really want here, right? If you're right in the middle, like this one example here, if you put your receiver right in the middle, then the path length is the same. Now, the example I got above, one path length was 3 full cycles, the other one was 4 full cycles, but the extra path length gave the wave that's traveling further a chance to complete itself in totality. And that's what allows them to be in phase here. And so down here where it's destructive interference, the extra path length, right? So this extra path length here, the extra path length is this right here, right? The bottom wave has got to travel that extra distance more. And that extra distance happens to be, in this case, a half of a wave. That's what put them out of phase. Up here, the extra path difference is that right there. The extra path difference there held an entire wave. And so they arrive now in phase. And if that makes sense to you, then you really kind of have this whole thing really figured out. There's really nothing more to it than that. So when it comes to constructive interference, so I'm trying to get you to think conceptually so it kind of makes sense that there is a extra path length typically, unless you're right between the two speakers, right? And so there's this thing called the path difference. And instead of writing this out all the time, typically your textbook will use the Greek letter delta. And if that path difference, that's the difference of one path minus the other path, and I'll kind of draw this out here in a second. If this is 0 or a whole number of waves, you've got constructive interference, where really M is a 0, 1, 2, 3, 4, any kind of counting number here. And so what we really mean here, to get the math to match up, this is a speaker. Here is one path, Here's another speaker. Here is the other path. But if I kind of came down here and I looked at the path difference, how much further R2 has to go than R1, if that can hold a whole wave right there, right? If a whole wave can fit here, then we have constructive interference. Okay, so the path difference, delta, is just the difference of those two numbers. And we just put absolute values there because we don't care that there's a minus sign. We just throw it away. One of them is longer than the other one. And so we just want to know that difference. If a whole number of waves can fit there, then they're going to arrive at this location right there in sync. And that's what you want. That's really the condition that you are really looking for here. Okay. And so if you have destructive interference, and I'm going to look at the pictures up above here to make sure that conceptually what is happening is making sense with our mathematics. The path difference, delta, so we have our two paths, we just subtract the two, has to be sort of on this order of a half of a wave, something like that. Half of the wavelength. And then we can have M up here. And M looks like to me could be a 1. Now, if I put M equals 2, 2 over 2 gives me a whole wave. That would be constructive interference. So it'd be like 1, 3, 5, 7. So it's going to have to be somehow, you know, the odd numbers or something like that. Okay. And so what that really means in terms of a picture here would be, you know, a speaker here. And we've got the spot here. So here's path 1. And we've got a speaker down here. Here's path 2. And path 2 is a little bit longer. And so, you know, let's say that a whole wave fits right here. So there's a whole wave. And then here's a whole wave. But now since this one down here is longer, there's a whole wave, there's a whole wave. But now the extra path length, right, the path difference right here has only space for a half of a wave, or it could be 1.5 waves or 2.5 waves or something like that. Now you've got the condition for destructive interference. So I think, you know, if you can get that to, you know, make some sense to you, then, you know, it's going to be exactly the same thing for something like light waves. Okay. So, you know, it might be kind of worthwhile here to, you know, just maybe look at a, you know, simple example or something like that here. And, but, you know, hopefully conceptually this is making sense and how that kind of turned into some mathematics here. So let's say, for example, I think I want to outline your study. Let's say that the frequency that's coming out of the box is 1000 hertz. Okay, and we'll use the velocity of the sound waves. It's pretty close to 340 meters per second every day. Okay, so, you know, what kind of wavelength am I dealing with? Because the wavelength really kind of tells you geometrically, that is spatially, where you can be to hit spots of constructive interference or spots of destructive interference. And I go back to this idea of distance equals rate times time, or I take out time and I put in, you know, the frequency. And so what I've got here is something like 340 meters per second, and my frequency is like 1000 hertz. So I have to move the decimal 3 places. So about 34 centimeters. So 1000 hertz, you know, we can hear this easily. Most people would have no problem hearing that. But, you know, the wave is something like 1/3 of a meter stick or something like that, pretty close to that. Okay. Now, if you have two speakers and they're both producing exactly the same frequency, you know, where could you be for constructive interference? One spot guaranteed would be, you know, someplace here, or that path and that path are exactly the same. Now there is no path difference, right? Now delta here is 0. No path difference. And if this happened to be something like 34 centimeters, and this was 34 centimeters, then we have a whole wave sitting. We have a whole wave right there. So they're completely in phase. This is a spot that is loud. This is constructive interference here. Okay. So this would be a spot of constructive interference. This is loud. What could you do kind of simply here to create destructive interference? Well, maybe what you could do, let me see here. If I want to spot destructive interference, what I might simply do is leave one speaker alone here. And let's say that this path is 0.34 meters. What I might do is get the other speaker and just move it back. And I might move it back like 17 centimeters. So that the top wave completes itself completely. But now I've got room for a half of a wave here, right? So if I move the other one back half that distance, or now the path difference, right? Delta is the path difference here. And one path is something like 34 centimeters. And the other one is 17 centimeters more than that. So it's 51 centimeters. What I get here is a difference that is this 17. And that equals half the wavelength. Hence, I'm going to get destructive interference there. So, play with these ideas and, read the textbook very carefully, work through some examples that we got here, work through the examples you got in the textbook, before you try to tackle stuff that you start seeing in chapter 16. And, you start building some foundation of understanding, typically those questions will go much easier for you, hopefully. So, some nice topics that show up in chapter 16 here. So this is pretty good stuff. So hang in there. I think we'll have maybe one more lecture on chapter 16, and at least for the sections that we'll cover in that. And you got any questions, just see me in discussion time or something like that. We'll try to take care of any questions you've got. But it looks like this is a good time to stop here, and we'll take a look at probably the Doppler effect and things like that, probably in the next lecture in chapter 16. So hopefully this helps you with some of the ideas there, and I'll see you soon.